Alright, we are now going to look at target 4A.2, and our master learning objective is I can calculate theoretical and experimental probability by creating a relative frequency table. So we've looked at simple probability. And when we're using simple probability, we actually have two different ways we use simple probability. The first one is theoretical, and that is probability based on mathematical reasoning. Then we have experimental probability, and experimental probability is probability based on doing an experiment. So for example, if we're talking about rolling a die, we use this as an example a lot. Theoretically, I can think there are 6 options, and rolling a 1 is 1 out of 6. Okay? If I actually go ahead and roll a die 10 times, right? So for experimental, if I actually roll a die 10 times, then I get a 1 twice. That probability is 2 out of 10, which is 1 out of 5. Okay, so those probabilities are different. So theoretical and experimental. Then we have, the next thing we're talking about is a relative frequency table, and we actually already made relative frequency tables. You know what these are. It's just a table showing frequencies, so that's like the count, how many times it happened, and probability. So for example, right, this survey or whatever asked what type of pet people have. There's a total of 56 people. So my frequency is 16, my relative frequency is just my probability. So that's 16 out of 56, which reduces to 2 out of 7. Right? Those are both divisible by 8. Same thing with cats, right? You would replace 28 out of 50. Oops. 56, which reduces to 1 out of 2. 8 out of 56, which reduces to 1 out of 7. 4 out of 56, which is 1 out of 14. And our total, we don't really find it. Okay. So these are my relative frequencies, and that's all a relative frequency table is. Again, we made one on Friday in class when you made your own survey question, right? So we've already kind of looked at those. So let's look at some examples. Example 1. Clara rolled a standard 6-sided die 50 times. She rolled a 1 6 times, 2 12 times, a 3 7 times, a 4 7 times, a 5 8 times, and a 6 10 times. Okay. So, this one was vertical. I like to create mine horizontally. We have what we're doing, so this is the number on the die. This should say frequency, not FREG, and then probability or relative frequency. I'm not going to be a stickler for which one we use. So we could get a 1, we can get a 2, we can get a 3, we can get a 4, we can get a 5, we can get a 6. Okay, this first one that we are creating is a theoretical. So I'm not actually doing anything yet. I'm just thinking about what could happen. So, how many 1s are on a 6-sided die? There's 1 of them. How many 2s are on a 6-sided die? There's 2 of them. Or sorry, there's 1 of them. How many 3s are on a 6-sided die? 1. How many 4s are on a 6-sided die? 1. How many 5s are on a 6-sided die? 1. How many 6s? 1. Okay, so this has nothing to do with what Clara actually rolled. That's the experiment she did. Theoretically, there's just 1 of each number on the die. So that gives us 6 total sides. So my probability for all of these is 1 out of 6. Okay, and that's it for your theoretical. For our experimental, right, the first part of our table is going to look very much the same. We still are using the numbers that we get. We should have the frequency, or the count, and the probability. So, I can have roll a 1, a 2, get a 3 on a die, a 4 on a die, a 5, or a 6. Okay? For experimental now, I am actually looking at what she rolled. So I'm going to look, how many times did she roll a 1? She rolled a 1 6 times. So under 1, I put 6. How many times did she roll a 2? 12 times. 3, I believe it's 7 times. I believe 4 was also 7. Right. 3 is 7, 4 is 7. She rolled a 5 8 times, and a 6 10 times. So you could add all these up to see what your total is, but the problem also tells you she rolled the die 50 times. So now I'm finding my probability here. My probability of a 1 is 6 out of 50, which equals 3 out of 25. Rolling a 2 is 12 out of 50. Which equals 6 out of 25. Rolling a 3 is 7 out of 50, which does not reduce. A 4 is 7 out of 50, which does not reduce. A 5 is 8 out of 50, which gives you 4 out of 25. And a 6 is 10 out of 50, which equals 1/5. Okay. So again, theoretical versus experimental. Different probabilities there. All right, go ahead, turn to the next page in your notes. Similar with example 2. Okay, so now we're looking at a bag of marbles. Rick picked up a bag of marbles, Inside there were 3 red marbles, 5 blue marbles, 1 yellow marble, and 2 green marbles. Then he had 25 different people pull a marble out of the bag without looking and put the marble back. The red marble was chosen 8 times, a blue marble was chosen 11 times, and a yellow marble was chosen 2 times. And a green marble was chosen 4 times. Okay? So, starting with our theoretical probability, what could I pull from the bag? I can pull a red marble, a blue marble, a yellow marble, or a green marble. Okay. So theoretically, how many red marbles could I get? Right? There are 3 of them in there. 3 red marbles in the bag. Theoretically, I can pull out 5 blue marbles. Theoretically, there's 1 yellow marble. And there's 2 green marbles. Again, that's before I pull anything out or I do anything. That's just how many marbles are in the bag. Okay. So there is a total of 8, 9, 11. I don't like the number. That's okay. 11 marbles. So the probability of red is 3 out of 11. Blue is 5 out of 11. Yellow is 1 out of 11. And green is 2 out of 11. Okay, so those are not equal probabilities, but it's still theoretical because no one's actually pulled a marble out of the bag yet. So B, now we're doing our experimental. Start with our color, our frequency, and our probability. Still the same colors, red, blue, yellow, green. Okay, so now experimentally, how many times could I choose a red marble? We chose it 8 times. When we did the experiment, we got blue 11 times, yellow 2 times, and green 4 times. Okay. So what are these probabilities? Again, thinking about our total. 8 plus 11 is 19, 21, 25, or again, 25 different people. So here we have 8 out of 25, 11 out of 25, doesn't reduce, 2 out of 25, doesn't reduce, 4 out of 25, doesn't reduce. So that's all right. All right, and that is it there. Looking at our last example, Bradley spun the spunner 40 times and recorded his results in the table. What is the theoretical probability of spinning green? Well, I have 1 green square out of 4 spaces. Okay, so theoretically, I get green 1 out of 4. What is the experimental probability? I have to look at what he actually did. He spun it 40 times. So we got 6 greens out of 40, which reduces to 3 out of 20. Right? If you think about what this is approximate, this is 0.25. And this one is 0.15, I believe. Okay, so these are not equal. Okay. What color had an experimental probability closest to its theoretical probability? Well, again, these all have equal theoretical. Equals 1 out of 4 for all of them, which is about 0.25, right? Which is 0.25. Blue has an experimental probability of 12 out of 40, which is Ugh. We can divide both of those by 4, so 3 out of 10, which is 0.3. Green, we already know is 0.15. Red is 9 out of 40. That does not reduce. Which is 0.225. And then white is 13 out of 40, which when you convert that to a decimal is 0.325. So which one of these is closest to 0.25? That's going to be red with 0.225. Okay. If Bradley spins the spinner 200 times, how many times would we predict the spinner lands on green? When you are predicting probabilities, we're going to use our theoretical probability of, right, it's probably about 0.25 here. Or times 1/4, whatever. And so we would expect 50 times. You could also, if all you have is experimental probability, you can use experimental probability to predict. That's what usually happens in the real world. But if you have a theoretical probability, you can use that as well. All right, that is it. I will see you guys on Monday.